And this, although this demand is unsatisfied by the current technologies, like in mobile phone batteries and portable power banks, in terms of its low power capabilities and the long time it takes to charge up. On the other hand, these two problems can be resolved by using what is called by the proton exchange membrane fuel cells, PEMFCs. These fuel cells provide the reliable and safe portable power supply. However, they are in the research stage now. There's a lot of studies that are taking place regarding these devices. One of the most important type of PEMFCs is the hydrogen-fed fuel cells. They have caught the most attention between all portable power supply methods due to the fact that they operate at a low temperature and the high power that they can deliver. The next slide, please, Ahmad. Here, the hydrogen atom fuel cells, the way it works is by electrolytic processes. The way it works mainly, a hydrogen atom, which is the fuel, is fed into the anode, which is then split up into one electron and one positive ion, which is the H+. This positive ion moves through the proton conducting membrane to the cathode. The positive ion then, which is the H+, can be combined with the oxygen to reach the cathode. This process will produce electricity and water as a byproduct. The water needs to be controlled and drained through and out of the cell to avoid dehydration and flooding in the circuit. Next slide, please, Ahmad. So the electrodes and their performance. Since this technology heavily depends on the electrolytic processes, scientists have searched for a good material to use as a catalyst in these anode and cathode. They have found that in low temperature and proton exchange conditions, the best material to use is platinum. The use of platinum has been approved in terms of system performance and durability. One good thing about platinum is that it can be recycled after its lifetime in the fuel cell, as only 2%, approximately 2% of it would be used during its lifetime in the fuel cell. Another thing about the anode and the cathode is that there are catalytic layers on the electrodes, which include carbon black supported platinum and Nafion ionomer. As we see here in the graph, we have two materials, A and B. A and B are two different materials that A, we found that it is a porous material which can let air pass through it, while B is less porous. So in material A, when the cathode or the anode are well aerated, they can let oxygen pass more easily. As convection is an important process in the electrolytic reaction. So A is more porous. We see in the graph that there are more convection, which is the current density, and therefore more voltage. While in B, it's less porous, so less voltage and less current density. When oxygen gets near the fuel cells by convection, by local air currents, or due to air circulation, which is natural convection, the outer layer of the cathode is called the gas diffusion layer, GDL. The selection of a proper GDL has a direct effect on the cell's performance, as in the figure. Next slide, please, Ahmad. So scientists have visualized the natural convection that we saw in the last slide. It was mainly around the cathode, using the shadow graphs, and have measured the gas diffusion layer, the surface temperature of the gas diffusion layer, and the accumulation of water at the cathode. They have found that the orientation of the fuel cell as well played a big role in the speed of air convection and the aeration and the oxygen, let's say, flux in the electrolytic process. So vertical cells have witnessed higher convection than horizontal cells, therefore homogenized cell temperature. Some designs which are fabricated using the low thermal conductivity materials have proved that they are effective at avoiding flooding by increasing the cell temperature and avoiding the dry outs of the cell by, as we said, the homogenizing of the cathode temperature. Next slide, please, Ahmed. So the materials and fabrication of the fuel cells. Mainly the fuel cells are manufactured by what is called by the additive manufacturing. More specifically, the process is called selective laser sintering, SLS. It is a method which is used to produce, it's done by the solidification of consecutive layers of powder on top of each other. Metals like stainless steel can be powdered and can be used in such technologies. It is found that the stainless steel is the best material to be manufactured by the additive manufacturing and the production of fuel cells. Stainless steel is also appropriate because it is corrosion resistant and has high toughness and hardness. These properties permit the cells to be reused many times. It also makes a good current collector because of its relatively low electric resistivity. We don't want an eddy current in the during electrolytic processes, and we want an efficient passing of the electrons between the cathode and the anode. Stainless steel is usually also coated with hydrophobic materials because, as we said, there is a byproduct of water in the electrolytic processes. So we need a hydrophobic material to protect the metallic components in the cell from corrosion and enhance the water management and avoid the flooding. Next slide, please, Ahmed. The hydrogen supplied to the fuel cell. How is hydrogen supplied to such a device that can produce energy? Hydrogen is mainly supplied in a manner called the dead-ended, in which hydrogen is supplied through an arrangement where maintaining relatively constant hydrogen pressure at the anodes. As we said, the gas diffusion layer on the anode. This constant hydrogen pressure can be achieved by supplying hydrogen through a valve. But one drawback to this is that this decreases the system autonomy, and it takes, in terms of cost and energy management, the valve needs to be controlled by a device. But how is the hydrogen is produced in this process? One of the attractive attributes of hydrogen is the versatility in its production. Pure hydrogen gas can be supplied in the anode, as it is here in the figure, and goes through the cathode, producing water as a byproduct, which is then controlled. Out of the circuit because of the hydrophobic material that is coated inside the fuel cell. Okay, now we'll talk about the production of hydrogen.
Okay, so as we said, hydrogen is versatile in the ways it can be produced. It can be produced from various sources, whether nuclear energy, renewable energy, or fossil energy, and also through different means, including electrochemical processes, thermochemical processes, photochemical, photoelectrochemical, or photocatalytic processes. And some of these processes have also carbon dioxide as a byproduct if it's produced from fossil fuel energy. However, if it's produced from renewable or nuclear energy, it is carbon-free.
Okay, so we're now talking about the steam reforming process. As you can see, this is a thermochemical process in which the chemical reaction reforms methane to produce an H2CO syngas. So the first step, the natural gas enters the system. Cleaning occurs where the sulfur is extracted from zinc oxide. Zinc oxide is used to extract sulfur to produce zinc sulfide. And then in the reforming process, we use it reforms methane to produce H2 with CO gas, syngas. After that, carbon monoxide can be used with water to produce even more hydrogen using water gas shift. After that, we capture carbon to reduce the harmful emissions to the environment. And finally, purification, where we extract all the hydrogen produced. And after purification, through pressure swing adsorption, we use it usually to produce hydrogen gas with up to 99.9% purity. Next slide, please. It is important to note that from this steam reforming process, the main product is hydrogen from 70 to 75%, while CO2 and CO are only produced from 6 to around 20%, which are then captured. CO2 is then captured, which decreases this percentage, and CO is then used to produce more hydrogen, which also makes it useful. And then methane is produced from 2 to 6%. Next.
Okay, another method of producing hydrogen is called gasification, which also relies on fossil fuels. However, this time we take coal and we gasify it in a chamber to produce syngas as well, that is made of hydrogen and CO. Okay, and we have to do the CO2, the desulfurization step to recover sulfur, as well as the CO2 separation step to capture the carbon dioxide for sequestration or for use in the industry. We can go through this process to produce other gases, like we can produce electricity directly from a gas combined cycle engine, or we can synthesize urea, ammonium, or methanol. However, we're going to focus on producing hydrogen, and this is also this process also produces carbon dioxide, but it can be sequestered to take care of it. And we also have the added production of hydrogen because of the use of CO to force the dissociation of further water molecules into hydrogen and carbon dioxide. Sorry.
The hydrogen from biomass. We can acquire hydrogen from biomass using several techniques. The first, we have fermentation, which is by the use of enzymes. We can also use gasification, which is through converting solid biomass, which is carbon-based fuel, into a gaseous combustible gas called producer gas through a sequence of thermochemical reactions. Then we can also perform this procedure using anaerobic digestion, which is in the presence of bacteria but lack of oxygen. In addition to that, metabolic processes can be used by using enzymes to disintegrate biomass into hydrogen, and fermentation is a special case of metabolic processing. High pressure supercritical conversion is the process of converting biomass to hydrogen at a supercritical high pressure condition. So it's basically just under high pressure. And finally, pyrolysis. It is the thermal dissociation of biomass into hydrogen in the absence of oxygen as well. Next.
Okay, now finally we're going to talk about a few thermochemical cycles for the production of hydrogen. The first one is the sulfur iodine thermochemical water splitting cycle, which consists of 3 equations. The first one concerns the dissociation of sulfuric acid into SO2, water, and oxygen. And then we add sulfuric acid to iodine to produce HI. This equation forms HI and reproduces sulfuric acid. So you can see that how sulfuric acid does not get consumed in this reaction. It's just recycled. And then we split hydrogen iodine into iodine and hydrogen. And the net reaction of these 3 reactions is just the splitting of water into hydrogen and oxygen atoms. Now, the hybrid sulfur cycle is similar to the first cycle, However, the second step is replaced by the electrolysis of water using SO2. So instead of using iodine, we start with the reaction is the same. It's the splitting of sulfuric acid into hydrogen and SO2, water and oxygen. And then the water and the SO2 are taken to a cell where electrolysis occurs to produce hydrogen. And this can cut on the energy requirements of the previous reactions because these reactions require heat as they are thermochemical methods. In the hybrid cycle, we can lower the required temperatures because of the use of electrolysis instead of another chemical reaction. And H2SO4 is also recycled in this cycle. This is an example of a hybrid sulfur cycle. We can see how the sulfuric acid first goes into the decomposer, which needs heat to decompose sulfuric acid into SO2, oxygen, and water. And then to a condenser to collect the water for the electrolyzer. The SO2 and O2 go through a separation chamber to get pure SO2 that can be used in the electrolyzer to produce hydrogen. And finally, the UT3 cycle is similar to the previous cycles. However, it is based on calcium, bromine, and iron. And it's also a set of 4 chemical reactions that would sum up to the dissociation of water to hydrogen and oxygen. This cycle is one of the most researched, and its efficiency has been greatly improved because of that. And now we're going to go to the hydrogen storage and transport.
Okay, so when we think about consuming hydrogen on a larger scale and actually using it in the industries, we have to pay attention to the storage and transport of hydrogen, since there are various techniques used for that, and much of them need a lot of improvement before they could be applicable on a very large scale, so that hydrogen could be used instead of the typical fossil fuels for energy. Okay, next. First, we are going to discuss the importance, technologies, and challenges of hydrogen storage. Why is it important for the fuel cell technologies to enhance hydrogen? Technologies vary from absorption, and carbon nanotubes, and challenges are mainly for storing high-density hydrogen, as we discussed earlier. Next slide, please. The importance of hydrogen storage. Hydrogen storage is considered a very essential aspect in enhancing hydrogen and fuel cell technologies in different fields, due to the fact that it has the highest energy per mass among fuels, but the problem is that it has a very low energy per unit volume due to its low ambient temperature density. Hence, we require updating the storage techniques to try to increase the energy density. And in addition to that, we have to include the various storage techniques in physical devices and in different materials, as demonstrated in the figure below. Ahmed. Okay.
I can't see the presentation.
Ahmed.
Can you share again, please?
Please refresh, Ahmed, the sharing.
Yeah, sorry. It seems that I disconnected for a second. Michelle Hall.
Yes, now we can see it. Yes.
Okay.
This slide علي أو اللي بعده؟
هاي خلصت اللي بعده. Okay. So this diagram shows us the various storage technologies of hydrogen. First, there are three methods for physical based: compressed gas, as we know it, cold or cryogenic compressed cryogenic temperatures for compression, and finally liquid hydrogen. For the material based, there is a wider variety. However, it is many of them are still under research, since if they are proved to be very efficient and can be used to store hydrogen, this could be the launch of hydrogen usage on a larger scale. These include chemical hydrogen, complex hydride, interstitial hydrides, liquid organic, and adsorbent, where chemical hydrogen and the hydrides are the most promising and have the largest potential if research went well for hydrogen storage. Next. Next, please. Okay. For physical storage, there are two forms: the gaseous form and the liquid form. For storing gaseous hydrogen, this requires highly pressurized tanks with a pressure range from 5,000 to 10,000 psi. On the other hand, to store liquid nitrogen, we need to provide ultra cold cryogenic temperatures, since hydrogen boils at a very low temperature, which is at minus 252.8 degrees Celsius. This deems both forms of physical storage challenging and require a lot of technology to keep the components of temperature and pressure under stable and working. Next, please. Okay, when talking about material-based hydrogen storage, there are two techniques. The first is absorption. Absorption is a condition where something takes place, where something takes in another substance, where the absorbent distributes the material it captures throughout the whole. Hence, we are integrating hydrogen within the solid itself, for example. On the other hand, adsorption occurs through storing hydrogen on surfaces of solids, which is the adhesion of molecules of liquids or gases onto the surface of a solid particle. Example, we can give a small example, which is graphene that can adsorb hydrogen on a solid surface with a 3.3% mass content if it is in the form of a sheet. However, if we mill the graphene to have shape of a ball, then we can increase this mass content up to 7.4%. This shows the importance of surface area and shape for storing hydrogen in the form of adsorption, using adsorption. To desorb hydrogen, there is a problem, since this requires a very high temperature, specifically over 600 Kelvin, which is 327 degrees Celsius. For adsorption, other materials are researched now, are being researched, such as magnesium, nickel, and boron. These elements are significantly lighter and better adsorb hydrogen, which is needed at high densities. However, the adsorption to these compounds requires also high temperatures and is very time consuming, which makes them impractical. Next slide, please. Due to these complications, we started searching for an alternative storage method, and we found a proposed storage alternative to be through the use of carbon nanotubes, which are unique due to their curved surface. This enhances the forces attracting hydrogen when the potential fields of opposing tubes overlap. However, there is a disadvantage due to nanotubes increased hydrogen uptake by 25%, which requires temperatures at around 100 Kelvin, which also makes it unsuitable for storage and vehicles and keeps it under research for further updates. On the right, we can see a very interesting 3D carbon-based nanotube matrix designed by researchers in Germany. This 3D carbon matrix can store and release hydrogen extremely efficiently. As we can see, hydrogen initially attaches at the points where the nanotubes touch. This doesn't occur when the nanotubes are placed alone and parallel, with the entire edge of each tube being in contact. So let's say we only have the yellow tubes and they are all parallel and in contact for a larger surface. This won't have higher hydrogen storage. However, when we have several tubes in parallel and only small portions being in contact, this is the place where adsorption occurs for hydrogen, and which is increased due to this design. The way these tubes are put together provides these points of contact, and the cylinders being put next to each other doesn't have the same effect. Next, please. Okay, so the challenges, as we discussed, there are several challenges due to hydrogen being still a new form of energy to be used. It's under research. The challenges to store high density hydrogen are due to our current storage methods, which use large tanks in volume and limits the storage to gaseous form. This is not a very major issue, since transitioning to compressed gas tanks won't have a large effect. Even though we can compress it, it still won't allow us to store a large amount of hydrogen compared to the gaseous form only. Well, the greater challenge is in portable applications in hydrogen. This is our main challenge in the case of fuel cell powered vehicles. Since hydrogen requires a large storage volume as a gas, fuel cell powered vehicles are limited by range due to the space requirement of gas. If the cars were larger, like larger vehicles, they are not affected as much, since they can have a larger capacity and volume. However, for small cars, we still have a problem which causes limited range and cannot be implemented. Next, please. Solutions to these challenges. To face this challenge, there are short and long-term strategies. For the short-term solution, we found out that hydrogen should be stored as a compressed gas in pressurized vessels consisting of fiber-reinforced composites that can withstand high pressures up to 700 bar. Also, our goal is mainly to reduce the cost of implementing this method by the time long-term solutions are accessible. For the long-term goals, we plan to transition to pressure vessels with cryogenic temperatures, which allow increasing hydrogen density. In addition to choosing material-based storage technologies, such as chemical hydrogen storage materials, sorbents, and metal hydrides, as I discussed before, but this requires further research. Moving on to hydrogen transport. We know that hydrogen must be transported from its production site to the end user, which necessitates a well-developed hydrogen infrastructure, including trucks, pipelines, compressors, and storage facilities. Many companies are able to actually supply bulk hydrogen, but infrastructure does exist in most developed areas due to hydrogen's significance in the industry. But however, this is not enough to consume hydrogen on a larger scale, since many other countries still have a lack of infrastructure that helps us transport hydrogen. Next, please. Okay, so as we can see, for hydrogen transport technologies, right now our current technologies include pipelines, storing hydrogen in cryogenic liquid tanker trucks, and gaseous tube trailers, by barge or by rail. For portable and stationary applications, hydrogen delivery is in cylinders or cartridges. Next, please. Okay, the challenges facing hydrogen transportation are mainly decreasing the cost of delivery, raising the energy efficiency, and reducing hydrogen leakage. Another issue would be establishing large-scale infrastructure for hydrogen transport, as I discussed, especially considering the regional variations in demand. So only developed countries are able to implement hydrogen usage more than third countries. Okay, next.
We're going to the applications of hydrogen. First, the fuel cell electric vehicles, and finally, applications of hydrogen in the industry.
So, since the hydrogen fuel cells took a big portion in the applications of the hydrogen as a energy source, we'll talk about the hydrogen fuel cells being applied in the futures cars. As we have discussed earlier, hydrogen is fed into the negative electrode, which is then separated into electrons and protons, which is the H+. Electrons take a path to a different external circuit, generating an electricity flow. This has opened doors for fuel cell electric vehicles, the FCEVs. FCEVs don't need to be recharged. They only depend on hydrogen. Next slide, please, Ahmad. We have different things that have faced the scientists while thinking about turning the future into the use of these electric vehicles. About refueling, stations store pressurized hydrogen. It takes 10 minutes to fill current vehicle models, and the driving range of the car is similar to the gasoline or diesel-filled cars, which is 200 to 300 miles. This has made the technology appealing for integration in larger vehicles and longer range requirements. This is easier in larger vehicles because, as Ali said earlier, we have a challenge in terms of the storage of hydrogen. So larger vehicles are more capable of storing a larger volume of hydrogen, therefore can go for longer range distances. These are the main challenges in this application. Although we have some applications of FCEVs the vehicles that are run on hydrogen and electricity in Japan and China more abundant than in third world countries, because they have better infrastructure of storing and transportation of hydrogen. Next, Ahmed.
Okay, now finally we're going to discuss hydrogen uses in the industry. We can see that hydrogen usage is distributed between 55% of hydrogen production goes to ammonia production, 25% goes to petroleum refining, 10% to methanol production, and around 10% to other applications. We're going to talk about ammonia production, electricity generation, steel manufacturing, electronics manufacturing, and the fuel production. Firstly, for ammonia production, we use hydrogen is usually produced on site via photovoltaic means from solar energy to produce CO2-free hydrogen, which goes to an ammonia production facility, a plant that produces ammonia, to produce carbon-free ammonia. The production of CO2 ammonia with a demonstration test plant using the ammonia synthetic catalyst developed in May this year. So we're going to have the next slide is going to discuss the process of converting hydrogen to ammonia. And then this ammonia can be used in an ammonia gas turbine to produce CO2-free electricity. Now, the ammonia production is through the Haber-Bosch process, which takes in hydrogen and nitrogen gases. They're fed to the reactor via a compressor. In this reactor, there are catalyst beds that allow the reaction of nitrogen and hydrogen to produce NH3, as there will remain unreacted nitrogen and hydrogen though. There's also a heater here, so we need a source of heat. Then they go to a heat exchanger, which reduces the temperature. Increases the temperature of the mix. They go to a condenser then the NH3 is separated from the N2 and the H2 gases, which are then recycled into the reactor to produce more NH3. And the NH3 has to be cooled. That's why we use they are placed in a refrigerated unit because it's often stored in liquid form. And this process allows